Reviews of Modern Physics. Volume 21, Number 3. July 1949. Kron's Non-Riemannian, Electrodynamics. Banesh Hoffmann. Queens Flushing, New York. College. This paper discusses some aspects of Kron's tensor theories associated with the use of non-holonomic reference systems in the mathematical treatment of rotating electrical machines. The general theory is discussed in the first part and is applied in the second part by way of illustration to a squirrel cage induction motor. 1. Introduction. The work of Gabriel Kron constitutes a significant enlargement of the domain of application of tensor analysis. In a previous paper, I considered that aspect of his work associated with his use of singular transformations. Here I am concerned with his discovery of the remarkable unifying role of non-Riemannian electrodynamics in the theory of electrical machines. Since the present paper is written for the mathematician and physicist rather than the engineer, it stresses theoretical issues to the neglect of the more practical aspects of the theory. 2. The general theory. For a dynamical system having degrees of freedom and generalized coordinates A, Lagrange's equations are d at R of x, where da, the generalized velocities, 7%, is the kinetic energy, r is the dissipation function, and f are the generalized impressed forces. Kron's method of subspaces, Quart, Applied Math 2, 218, 1944, see also a mathematical interpretation of some work of Gabriel Kron, published in mimeograph form by Brown University, 1943. See his fundamental paper Non-Riemannian Dynamics of Rotating Electrical Machinery, Journ. Math, Phys. 13, 103, 1934. A full bibliography of Kron's publications was given by S. Austin Stigant in Biema Journal, August 1948, under the title Gabriel Kron on Tensor Analysis, a bibliographical record. This is included because of the electrical situation later. The introduction of a Rayleigh dissipation function in this way in mechanical problems is usually only an approximation. The kinetic energy T is a quadratic function of the velocities and, under usual circumstances, a homogeneous quadratic function whose coefficients are functions of the coordinates A only. We consider only this latter case and write T equal to. For the dissipation function we may write R equal to R. Here, Lu, R are symmetrical in S and I and are functions of the coordinates. It is well known that the motion of the dynamical system may be represented by that of a point, having coordinates in an n-dimensional Riemannian space with metric LA. The path of this point is given by the dynamical EQ, 1, which may be written in the tensorial form, laut, it, plus R1st, equal to F, the comma, denoting the covariant derivative with respect to the Christoffel symbols formed from the metric L, more specifically, 4, may be written. Luxt plus 1, 3t2, plus R and equal to F, where 1 L Limi axt dx dx. Maxwell showed that the Lagrangian dynamical equations could be applied to electrodynamical problems if, in addition to mechanical one, included electrical degrees of freedom, say m of them, described by m, coordinates are measuring the total amount of charge transported across a given point in each independent. 536. Banesh Hoffmann. Electrical circuit from an initial time to any time. The quantities, which in dynamics would be called generalized velocities, are here the currents in the various independent circuits. For certain electrodynamical systems, the kinetic energy has the form T equal to L, AA plus L. A, B refer to electrical degrees of freedom and S to mechanical. Maxwell showed that in macroscopic investigations, mixed terms of the type will not appear in T. The quantities last measure the self and mutual inductances of the various electrical circuits. They measure such quantities as masses and moments of inertia. The electrical dissipation tensor, which we may denote by RAS, measures the electrical resistances in the various circuits. The mechanical dissipation tensor R refers to mechanical dissipation of energy, but since a mechanical dissipation tensor can adequately represent an actual situation only under special circumstances, we shall here take the mechanical dissipation tensor to be 0. The L's and R's, whether electrical or mechanical, depend only on the mechanical coordinates and do not contain the electrical coordinates A, nor do they contain the generalized velocities too. When saturation and analogous phenomena are taken into account, this is no longer true, but such matters are outside the scope of the present discussion. In geometry, the permanent absence of specific coordinates from the components of all geometric objects is called a cylinder condition. Thus, in the plus-dimensional space having coordinates A, AMAS, there is a cylinder condition associated with the M electrical coordinates. Using Greek indices AB for the range AS, we may write the Lagrange-Maxwell electrodynamical equations in the same form as 1, 4, or 5, with these Greek indices replacing the Latin indices there used. Thus, the behavior of an electrodynamical system may be represented by the motion of a point in an plus-dimensional Riemannian space in which M of the coordinates obey a cylinder condition. The metric is Lass, where, that is, provided the S represents simple currents in individual circuits. Naturally, if a general transformation were made on the S, the LRCs would lose this simple physical significance. An analogous situation exists in the purely mechanical case. The dissipation tensor Ras here has the corresponding form B1 R Ras X 0 R1S equal to 0, 0. In the theory of rotating electrical machines, one has occasion to introduce a non-holonomic reference system of a special type. The transformation leading to this non-holonomic reference frame is always of the restricted form D2 equal to Cx plus dx 2 to 2x, in which the mechanical coordinates transform holonomically while the electrical differentials transform by means of a matrix depending only on the mechanical coordinates. For our present purposes, we may take this to be of the simpler form. In a holonomic reference system, all geometric objects are represented as functions of the coordinates x. In a new holonomic system, they become functions of the new coordinates instead of the old. In a non-holonomic reference frame, however, we do not have a complete set of new coordinates, we have only a set of new differentials. Thus, relative to a non-holonomic reference system, geometric objects are expressed as functions not only of the new differentials, but also of the old coordinates. In general, one must carry the original holonomic coordinates along with the new differentials. In the present situation, owing to the cylinder condition and the special nature of the non-holonomic transformation. 11, as also of 10, the geometric objects may be expressed without the aid of the old coordinate system. For that part of the old coordinate system, namely A, which alone enters the expressions for geometric objects, is precisely the part that is transformed holonomically. Consequently, there will here be nothing in the appearance of the transformed geometric objects to characterize them as being in a non-holonomic reference frame. This allows us to regard all geometric objects in the new non-holonomic reference frame as belonging to a holonomic system, say with coordinates, in a new space differing from the original Riemannian space of X. There will be a cylinder condition on the M electrical coordinates in the new space, and under 11, the mechanical coordinates in the new space will be the same as those in the old, that is, A, or Non-Riemannian Electrodynamics. 537-37. The metric of the new space will be L, obtained by transforming the original LAs according to the usual tensor law. Specifically, if we write 11 as, where C2 has the form C1, X2, 0 electrical 0 mechanical electrical me, chanical, and if we denote the inverse of CA by CX, the new metric is given by Lau X equal to CXOC plus. However, as Kron pointed out, the new space is no longer Riemannian. For the law of transformation of connection is A TGCCTC X, whether the transformation is holonomic or not. In the present case L, are Christoffel symbols formed from the metric as, namely, by A, owing to the special character of the transformation, 11, and the cylinder condition on the electrical variables, it is here possible to form Christoffel symbols, from the new metric L from 15 and 16, and the definition of the Christoffel symbols, it turns out that the original Christoffel symbols, Bayer, do not transform into the Christoffel symbols Kerr, but into a connection Tx given by, where ACX RQ ACA, This quantity usually depends on the original coordinates. But here, as has already been explained for any geometric object, we may express in terms of the new variables. Let us replace c, 0, 0th, by its equivalent a, this being valid since we are operating on quantities c which do not contain electrical variables. Then we may write equal to Lc vac arc t. Under any holonomic transformation on the variables 2, the quantity behaves like an ordinary tensor. We consider the wholly covariant form IGY, lay since its law of transformation contains c but not c. There are important occasions in Kron's general theory when singular transformations are employed in which c is defined but not c. Fig. 1. Single-phase induction motor. Of the third rank, since such a transformation will not affect the index a, and for each, a the expression in parentheses has the form of a curl. Thus, when we choose to regard the new system as holonomic, we find ourselves in a metric space having a connection given by 17, where the quantity behaves like a tensor. This new connection f is clearly non-Riemannian. The covariant derivative of the metric with respect to it is still identically 0, for t is the transform of the Christoffel symbols by a, which satisfy, and under 11, this must transform into lo, where the solidus denotes the covariant derivative with respect to the new connection. To sum up, we start with a holonomic reference frame in a Riemannian space. When we go over to a non-holonomic reference frame of the special type here discussed, we have the choice of regarding the new system either as a Riemannian space, referred to a non-holonomic reference frame, or else as a non-Riemannian metrical space, with torsion, referred to a holonomic reference frame. 3. Application to squirrel cage induction motor. To show how non-holonomic transformations of the type discussed above enter in practice, we discuss the simple case of a single-phase squirrel cage induction motor. The generalization to more complicated situations is straightforward, but the basic physical discussion is a little different for phase wound rotors, while the extension to commutator machines introduces special problems. A single-phase squirrel cage induction motor is illustrated symbolically in Figure 1. It consists of two parts, a stator coil and a cylindrical rotor, the shape of the latter being best described by its name squirrel cage. The rotor is free to rotate about its cylindrical axis. The stator remains stationary, and into it is fed an alternating electromotive force. For clarity, the stator coil has been drawn in the wrong position. In practice, it is larger than the 538. Banesh Hoffmann. Fig. 2. Moving current paths on moving rotor. Rotor and circumscribes the latter. The crossbars of the squirrel cage are welded to the end rings, and there is no metallic electrical connection between rotor and stator, the stator influencing the rotor only by electromagnetic induction. The rotor is rigidly connected to its own axis of rotation, but this connection is omitted from the figure. The problem is to set up electrodynamical equations of motion for the performance of the machine. In doing this, certain simplifying assumptions are made. For example, rather than treat each crossbar of the rotor separately, engineers assume that the whole squirrel cage may be adequately represented by a pair of mutually perpendicular closed coils, as in Fig. 2. Since the rotor is symmetric, there are no preferred positions for these coils, so we may imagine their positions on the rotor determined arbitrarily, say by marks made on the rotor. The electrodynamical system illustrated in Figure 2 has 4 degrees of freedom, 3 electrical and 1 dynamical. The corresponding 4-dimensional space has coordinates A, where A has the range 1 to 4. We label the stator coil Coil 1, and the 2 rotor coils Coil 2 and Coil 3 respectively, and denote by the angle that one rotor coil makes with the fixed plane through the axis of rotation perpendicular to the axis of the stator. Then we may write, where A are the total amounts of charge transported respectively in the circuits 1, 2, and 3 from time Li to any time 4, and A stands for the geometrical coordinate 0. The corresponding velocities are, where the I's are the currents in the 3 circuits, and is the angular velocity of the rotor. The dissipation tensor is diagonal and has the form. Hira is the resistance of the stator winding, and R is the resistance of each of the rotor coils 2 and 3. These having equal resistances on grounds of symmetry. Here, The constant I is the moment of inertia of the rotor about its axis. Las is the self-inductance of the stator winding, which is a constant, and las are the mutual inductances between the stator and the respective rotor coils. Las are the self-inductances of the rotor coils, and las their mutual inductance. Induction motors are not so constructed. Other motors do have such. Let us pretend that the stator has a salient pole, even though in poles. The salient pole introduces an asymmetry in the air gap between rotor and stator. Were the air gap symmetric, LAS would be 0 and LAN would equal LA. But the presence of iron influences inductances, and so for the present, we shall leave these L's as unspecified functions of 0. If the EMF impressed on the stator winding is denoted by S and the mechanical torque load imposed on the rotor is denoted by G, the generalized force vector is φ 0, 0, G. The zeros enter because no EMFs are impressed on the rotor coils, induced EMFs being taken care of by the inclusion of the inductances. It is now a simple matter to substitute the above values in the Lagrange-Maxwell equations, dRc, where, and T r rast. This will give us the equations of motion for the machine. They will be of two types, electrical and mechanical. The former, called the equations of voltage, arise when A has the values 1, 2, 3. The latter, called the equation of torque, is that for which A has the value 4. If proper assumptions were made concerning the functional forms of the various inductances, the equations of motion would be ready for solution. The procedure just outlined pertains to a holonomic reference system in a Riemannian space. Now, however, let us approach the matter from a different point of view. In replacing the squirrel cage rotor by a pair of mutually perpendicular coils which rotate with the rotor, as if rigidly attached to it, we were essentially picking out two mutually perpendicular current paths on the rotor and endowing them with such inductances and resistances as would enable them to represent, with sufficient accuracy, the electrical properties of the rotor as a whole. Suppose now that we represent the electrical properties of the rotor by two mutually perpendicular current paths much as before, but with the important difference that they shall be stationary. Such current paths, or coils as we shall call them, will not be rigidly attached to the rotor, and we cannot imagine them to be made out of some particular portion of the Non-Riemannian electrodynamics, 539, metal forming it. On the contrary, we must imagine a continual metallic metabolism to be taking place in the constitution of these coils. The coils are fixed, but their metallic constitution changes as the rotor rotates. While this change of viewpoint may seem artificial in the case of a squirrel cage induction motor, it is often essential in more complicated situations. For instance, when a motor has stationary brushes, these define stationary metabolistic current paths on the rotor that are of fundamental importance. Even in the present, simple case, we shall be able to see some of the significance of the new viewpoint. If we neglect the minor fluctuations arising from the existence of gaps between successive bars of the squirrel cage, we must expect all the inductances of our stationary rotor coils to be constants. Engineers naturally prefer constants to more general functions. They call them design constants, and determine their numerical values either by actual measurement on the machine under investigation or by calculation from a detailed drawing of it. The present machine, with its stationary rotor coils, has 4 degrees of freedom. Denote the corresponding coordinates by the coordinates 2. 2 have the same meaning as A before. Thus, if we take the new, stationary coils 2, 3, in the position shown in figure 3, measures the angle, E, between coil 2 and the previous coil 2, and likewise between the coil 3 and the previous coil 3. The coordinates refer to the stationary coils 2, 3, and are such that the corresponding velocities flowing in those coils are the currents. The metrical tensor must here be 1I2 3 trillions lala 0 to 100 and 4 3 lula 0 0 3 0 0 0 0 0 1, where all the L's are constants. There will be no mutual inductance between the 2 and 3 coils even if a salient pole does thread the I coil on the stator, for we are taking 3 in line with the salient pole and 2 perpendicular to it. However, the presence of the salient pole makes L and LAS unequal, even though the rotor is symmetric. It was in order to show the effect of this type of inequality that we pretended there was a salient pole. To find the relationship between the new reference system and the former reference system, we make a simplifying as sumption. The mutual inductance between two plane circuits has its greatest numerical value when they are parallel and falls to 0 when they are perpendicular. Although the actual mutual inductance is a complicated function of the angle between the two circuits, it is a standard engineering approximation that near the centers of the coils the mutual inductance varies as the cosine of this angle. We make that assumption here, since the mutual inductance of two circuits measures the magnetic flux threading one circuit when unit current flows in the other. This assumption amounts to taking the relevant parts of the magnetic fields of the plane coils to be uniform and perpendicular to the planes of the coil. We wish the pair of coils 2, 3 to have the same electrical effect as the pair of coils 2, 3. Therefore, for instance, we want the magnetic flux through circuit 2, due to the currents in 2 and 3, to be the same as the magnetic flux through this same circuit 2, due to the currents 2 and 3. The former flux is measured by LA. The latter is measured by L plus L, where L are the mutual inductances with 2 of 2 and 3 respectively. Fig. 3. Stationary current paths on moving rotor. Question have the same shape we have by the simplifying assumption above, since all the circuits in Li Li cos 0 plus 90 deg equal to Li sine J10. Hence, La cos lisine, or, since Liege is not 0, cost sine. Similarly, by considering the flux through 3, we find that S sin plus cost, combining 32 and 33, and the relations μ we have 34. This is a tensor transformation on the velocity vector 2a, and since we require the kinetic energy to be the same whether we use coils 2, 3 or coils 2, 3, we see from 27 that Lass must here transform as a covariant tensor of the second rank, that is, now lag, and are tensors in virtue of the role they play in the Lagrange Maxwell equations, so that if the S undergo a tensor transformation of the type 34, 35, the L's must undergo the corresponding tensor transformation 36. We could always make the tensor transformation 34, 35, 36, but without some such discussion as that above, we should have no way of interpreting it as a transition to stationary coils 2, 3, and thus no grounds for taking all the new components LA to be constants. Were it not for the simplifying assumptions made, particularly that the mutual inductances varied as the cosine of the angle between the coils, the transformation 34, 35, 36 would not correspond to a transition to stationary coils 2, 3. Nor would a transition to stationary coils 2, 3 correspond to a tensor trans. 540. Banesh Hoffmann. Formation in general. However, in engineering it is usually sufficiently accurate to make the above simplifying assumptions, and when greater accuracy is desired the engineer introduces harmonics. Kron's tensor theory is valid for each harmonic. Let us return to the transformation 34, 35 on the 2s. This is essentially a relation between differentials. D equal to Sadar. Since, by 35, the transformation is non-holonomic, consequently we must use Kron's non-Riemannian form of the Lorentz-Maxwell equations. These equations may be written last in T plus rent equal to Px. The solidus denoting the covariant derivative with respect to the non-Riemannian connection F, defined in 17 and 18 or 19 and 22. Owing to the antisymmetry of, in the first two indices, 4 may be written, which is the same as, at R, comparing 1 with 1 or 26, we see that the essential difference is the entry of the additional term 2a. We have T, where LA is given in 29. Also, R, and from 23 and 35 we see that has the same components as RAS. If we use these values of T and R in the original form of the Lagrange-Maxwell equations, 26, we would obtain wrong results. We must use them in the generalized form. 1. However, the ordinary Lagrange-Maxwell equations, 26, would give correct results if we used the appropriate form, 24 of the metrical tensor LAS. It is of interest to see what the simplifying assumptions made above imply in terms of the form of 24, transforming from the constant low back to the LAAs in the holonomic frame by means of the tensor law. With a given by 35, we find that 1 li cos, li sine 02, li cos la locos 29, lo sin 2003, li sinella sin 29 ls plus locos 2040. L equal to L plus L, lo equal to li. If the air gap is symmetric, li, and so lo is 0. In this case, the components la, las of lad vanish, and this means there is no mutual inductance between the moving coils 2, 3 on the rotor. When there is a salient pole or other asymmetry in the air gap, this mutual inductance will not vanish. The above has touched on only one of the many aspects of Kron's work. His various tensor ideas have a wide range of application. They cover such things as the theory of stationary electrical networks, the interconnection of complex systems, whether electrodynamical, mechanical, or hydrodynamical, the hunting and stability of all such systems, and the setting up of equivalent circuits, not only for their performance under different conditions of operation, but even for the partial differential equations of classical and quantum physics, the engineering term for small oscillations about steady motion.